Hello students, so today we will have a comparison of SN1 and SN2 reaction. So SN1 reaction, substitution nucleophilic unimolecular. So it is a unimolecular reaction. Whereas SN2 which is substitution nucleophilic bimolecular is a bimolecular reaction. And in SN1 reaction it follows a two-step mechanism. So in the first step it forms a carbocation. The second step the nucleophile comes and attacks the carbocation. We have already learned it in the last video. And then in SN2 it is a concerted single step mechanism. So in this, the nucleophile attacks backside and the ring group leaves from the front side. So it takes place in single step. So it is a concerted reaction. Okay. And then in SN1, it depends on concentration of alkyl halide. Actually, it depends only on the concentration of alkyl halide. So it follows first order kinetics because it depends on concentration of one substrate. Okay. So you write the rate expression as rate equal to Krx. Here the square bracket denotes concentration. So it denotes concentration of rate depends on the concentration of Rx. Okay. And whereas in SN2 it depends on concentration of alkyl halide as well as a nucleophile. So it follows second order kinetics. So it depends on two substrates. Okay. Two reactants on both the reactants. Okay. So it follows second order kinetics and you write the rate expression as rate equal to Krx and Nu. So it depends on concentration of Rx and depends on concentration of nucleophile. Okay, and K is a rate constant. And then moving on to reactivity order. So in SN1 reaction, the reactivity order goes like tertiary, secondary, primary, and methyl halide. So tertiary alkyl halides are more reactive towards SN1 reaction. Okay, and the reason is carbocation stability. See, I have already discussed it in the last video. That is, for tertiary alkyl halide, you have three alkyl groups attached. So when three alkyl groups are attached, the carbocation will be stabilized by the three alkyl groups, by the plus I effect of the three alkyl groups. So it will be more stable. So that is the reason since tertiary carbocation will be more stabilized in the case of tertiary alkyl halide. So tertiary alkyl halide will be more reactive towards SN1 reaction. So this is the order. So you write this reactivity order based on the carbocation stability. Whereas in the SN2 reaction, methyl halide will be more reactive towards SN2, then comes primary, then secondary, then tertiary alkyl halide. So it is based on the steric effect. So the steric effect it is because, as I told you, it takes place in a single step. So attack and leaving takes place in single step. So when there are, in the case, if you look in the tertiary carbocation, there will be three alkyl groups. So it is a bulky. So one, already alkyl group is a bulky group. So when three alkyl groups are present, there will be bulkiness. So when three alkyl groups are present, it will be difficult for a nucleophile to come and attack. So due to this recent experience of steric effect, there will be a steric hindrance, and due to this there will be a steric effect. And due to this reason, tertiary alkyl halides are less prone to SN2 reaction because of that steric hindrance. So that is the reason why methyl halide is more reactive towards SN2, then primary, then secondary, then tertiary. Then in SN1, as I told you, there is a carbocation intermediate. Whereas in SN2, there is no carbocation intermediate. What you have is a transition state. In transition state, which has in this transition state you have carbon oxygen bond formation and carbon halide bond dissociation. So here you have the transition state and there is no carbocation intermediate for the SN2. Okay. Then for SN1, if alkyl halide is optically active, retention and inversion of configuration takes place, forming a racemic mixture. Actually, optically active compounds, we will discuss it in detail in the next video. Actually, optically active compounds are compounds which can rotate plane polarized light. Okay, so if the alkyl halide is optically active, in the case of SN1, there will be retention and inversion. See, carbocation is basically a planar structure. It has a planar structure. So basically, the nucleophile can attack from front side or back side. Okay, so both the ways are possible. So it forms. So since both side attack is possible, two equal proportions will be formed. You call it as DNL isomer will be formed. So that is why there is retention as well as the inversion of configuration. Retention, basically it will retain the configuration of that reactant. So then it will be a retention, and if the configuration inverts, then you call it inversion of configuration. So since that is like 50-50 proportion, then that is the reason we call it as racemic mixture. When there is 50% D isomer and 50% L isomer, then it forms a racemic mixture. Okay. Then in the case of SN2, there is only inversion of configuration. You can also call this value inversion. I have discussed about this in the previous video. Then in SN1 reaction, weak nucleophile is preferred. Weak nucleophile is preferred, whereas in SN2, strong nucleophile is preferred because it takes place in single step, as I told you, SN2. So the nucleophile must be strong enough to push that leaving group from that substrate. Okay. Then SN1, polar protic solvents like water, ROH is preferred. Actually, polar compounds, they have electronegativity difference. And protic solvent in the sense when hydrogen is attached to a electronegative atom. In such cases, we call this protic solvent. So when hydrogen is attached to electronegative atom, example oxygen, so there will be an OH bond. So that will due to this reason there will be a hydrogen bonding. Okay. So when hydrogen is attached to an electronegative atom like oxygen, and then there will be hydrogen bonding. Such solvents we call as protic solvents. So in the case of water, you can see hydrogen is attached to electronegative atom oxygen. So in this case, hydrogen bonding is possible. So such solvents you call it as protic solvents. Okay. So SN1 reaction, you prefer polar protic solvents like water and alcohol, ROH meaning alcohol. And in SN2 reaction, polar protic solvents like acetone, DMSO. So in this case, like hydrogen bonding won't be present and hydrogen won't be attached to any electronegative atom, like directly. In this case, directly. See acetone. Here you can see acetone has a structure. See, here hydrogen is attached to carbon, but it is not attached to oxygen. So here hydrogen bonding won't be possible. So such solvents you call it as polar aprotic solvents. Okay. So that's it for the comparison between SN1 and SN2 reaction. Now we will discuss a few questions related to SN1 and SN2. So first, reactivity towards SN1. So we know SN1 as tertiary, secondary, primary. Yeah, this is a reactivity order. So in this case, you can see carbon attached to this carbon attached to 3 carbons. So this is tertiary, and this carbon attached to 2 carbons. So this is secondary. So basically, SN1 tertiary substrate will be tertiary alkyl halide will be reacting faster. So this will be more reactive. Then in this case, this carbon attached to 2 carbons. Okay. So this is secondary, and this halogen attached to a carbon, and this carbon attached to 1 carbon. This is primary. So you can see this is primary, and this carbon is secondary. So basically for SN1 reactions will be more reactive. Okay. So I hope this is clear. This is primary and this is secondary. So this will be more reactive. Okay. And SN2 reactive. Now we will discuss about SN2 reactivity. Okay. So in this case, this halogen is attached to a carbon attached to 1 carbon. So this is primary, and this halogen attached to a carbon attached to a carbon. So this is secondary. So for SN2 reactions, primary, then secondary, then tertiary. So in this case, this is the order. So since this is primary, so this will have a higher reactivity. Okay. And in this case, you can see that CH3 ion, CH3 Br. See, iodine is a good leaving group. So in SN2 reactions, basically iodine is a good leaving group. So due to this reason, this reaction will proceed faster. Like the substrate having this alkyl halide. Okay. So this will have more reactivity, and then in this case you can see this is attached to carbon, this is attached to 1 carbon, so this is primary. In this case attached to 2 carbons, so this is secondary. So basically this will be more reactive for SN2. And so one thing, see here you have methyl group attached. Here also you have methyl group attached. When there is methyl group nearby, what happens is that there will be a steric hindrance. Okay. So due to all this reason, this will be reacting faster, primary. This methyl group is far away, whereas this methyl group is near to it. So here the reaction will be slower. Okay. And in this case, this is tertiary, this is primary. So basically, this is the order.